Hello and welcome to another video in the series where I've been building experiments from Charles Platt's excellent introduction to electronics, Make Electronics. In the previous two videos, the book has introduced us to logic chips. And today we're going to see how logic chips can be used to solve a very common but often hidden problem that you might encounter with switches.
So to illustrate the problem, I have here a very simple circuit and it's powered by the 5-volt regulator that was introduced back in the video for experiments 19 and 20. And here we have a single pole double throw switch, and either side of this switch is connected to a single LED. So if I power up the circuit now, you'll see that one of the LEDs is on. But if I throw the switch to the other side, then that LED goes off, the other LED comes on, and vice versa. So apart from not being a particularly interesting circuit, this works perfectly, right? Or does it?
Let's look at what's happening with the signals in the circuit. If we start with the slider contact connected to the lower terminal of the switch, then the signal to LED 1 is going to be low, while the signal to LED 2 will be high. When we slide the switch contact across to the top terminal, then the signal to LED 1 will go high, while the signal to LED 2 will go low. And when we slide it back again, the opposite happens. That's what we expect, right? That mirrors what we're seeing with the naked eye when we look at the LEDs as we operate the switch. But appearances can be deceptive. No switch is a perfect device, which means that a combination of vibration and imperfections in the switch will mean as you slide the switch, the connection between the slider contact and the terminals could be momentarily broken and remade several times over a short period of time. The same thing will happen when we slide the switch back. This behaviour is known as bouncing because of the way the signal bounces back and forth. Now, if we're just using the switch to light a couple of LEDs, do we care? Probably not. As we've seen, the effect is too quick to be visible to us. But there will be applications where we do care, especially in digital electronics. Imagine if one side of the switch was connected to a series of decade counters that were being used to count circuit activations. Instead of a single count when the switch changed, depending on the characteristics of the decade counter, we might record multiple counts each time the signal bounced. Solving this problem is known as debouncing the switch. To do this, the book introduces a new logic gate, the NOR gate. The symbol for this gate is the same as an OR gate, but with the addition of a circle on the output. If we look at the truth table for a NOR gate, you can see that it's essentially the inverse of an OR gate. For an OR gate, the output is low when both inputs are low and high otherwise. But for a NOR gate, the output is high when both inputs are low and low otherwise. The design in the book uses two of these NOR gates connected together to form a flip-flop. This isn't the first time the book has introduced us to a flip-flop. We actually used an analog flip-flop built with discrete transistors for the multivibrator circuit back in experiment 11. The type of flip-flop we're creating now, though, is known as a NOR latch. An important thing to notice is that the output of each gate is connected to one of the inputs of the other gate. That means there are only two inputs to the latch. Traditionally, these are labelled S and R, which stands for set and reset. The two outputs are labelled Q and not Q, or bar Q if you prefer. Let's see what's happening in this circuit when we have our switch in the lower position. Note that each of the inputs S and R are connected to the ground bus via pull-down resistors. In the case of S, because its switch terminal isn't connected, the pull-down resistor will pull it low. For R, because its switch terminal is connected to the positive supply bus, that pulls R high. If you recall from the truth table, the output of a NOR gate can only be high if both inputs are low. Because the R input is being pulled high, that means the output of this NOR gate must be low, regardless of what is happening with the other input. So the output not Q is going to be low, which means both inputs to the other NOR gate will be low, and correspondingly the output Q will be high. Let's now start to slide the switch across. As we now know, as the sliding contact travels, there may be times when it momentarily loses contact with the lower terminal, meaning at that point neither terminal is connected to the positive supply bus. That means that R is going to be pulled low by the pull-down resistor. However, because the other input to this NOR gate is still high, its output, not Q, is not going to change. It will still be low, meaning both inputs to the other NOR gate remain low and its output Q is also unchanged, remaining high. As the sliding contact in the switch continues to travel, it will eventually connect to the upper terminal, meaning that S is now connected to the positive supply bus. Because S is now high, the output Q must be low. Meanwhile, R is now connected to ground again. And because the other input is connected to Q, which is now low, both inputs to that NOR gate are now low, meaning that not Q now goes high. And likewise, if we start to slide the switch back again, there may come a point where once again neither switch terminal is connected to the positive supply bus, which means both S and R will be low. But because the other input to the NOR gate for S is held high, there will once again be no change to the output states. Let's look at our switching sequence once more and see what difference this makes to our bouncing problem. We start with the switch in the lower position, meaning R input is high. So the LED connected to Q is lit and the LED connected to not Q is unlit. As we start to slide the switch, any bouncing on the switch terminal connected to R is not going to have any effect on the output states. But as soon as we get our first rising edge on the terminal connected to S, then the states will switch and the LED connected to not Q will be lit. Likewise, as we slide the switch back again, any bouncing on the S input will have no effect, but as soon as we get our first rising edge on R, the circuit will flip back again. Okay, let's see that in action in the built circuit.
So here's the same circuit, but now with that flip-flop, the NOR latch in place. And what you'll be able to see is that when I throw the switch, again, we switch over from one LED to the other and back again. Now, just looking at it like this, you might be wondering, well, is that NOR latch really adding much because we're getting exactly the same functionality as we got before? But actually, we've got a much more stable circuit here because as soon as we throw that switch, then the NOR latch is changing the state of the circuit to light the other LED, and it's holding it there, and that is the key point here. And just to demonstrate that, if I now throw the switch back again, you see the state we're in now is with the lower LED lit and the upper LED unlit. And at this point, I can even completely disconnect the switch. And as you can see, the latch is holding that steady state. And that's really the functionality that it's providing us with that can be useful in debouncing a single pole double throw switch like this.
I hope you found that interesting. We're now at a point where we can put all that knowledge about logic chips to use to build a complete project. So in the next episode, I'll be building the book's design for an electronic version of this, a standard 6-sided die. So please join me for that. See you then.